welcome to the 37th class in this course, the physics of materials. Through this course in several of our early classes we have developed the framework and the theories with which we can attempt to explain material properties and phenomena that we see when we investigate materials or we work with materials. And over the past few classes we have actually started looking at various throughout the course itself we looked at specific properties, but we have expanded the scope in the past few classes. We are looking at several properties and seeing how the framework that we have built is something that we can apply to these properties and understand what we have or apply it to the phenomena that we see and understand what we have. So we will continue in the same vein in today's class. We will actually look at a particular we will actually look at compounds that form. We will look at something that we see in certain types of phase diagrams and certain phenomena we see with respect to when phases form and what is causing them to form. So this is something that we will look at right now. We will look at the phases that form and what is the driving principle behind those phases that form. What we are going to discuss applies to a certain type of compounds only, certain types of phases. So it is restricted to that set of phases. So we will so please bear that in mind as we look at the discussion. Okay. So it turns out that if you look at say silver, okay, and copper, it turns out that when you look at various binary phase diagrams of silver and copper, several binary phase diagrams you look at, you find one general phenomenon showing up. See, these two are both FCC structures. So at room temperature they are FCC, and if you take many binary systems based on this, so you are adding one additional alloying element to this and you start looking at the phase diagram, you invariably find that the terminal solid solution is since this original structure, a terminal solid solution is the solid solution that you have very close to the pure component. Okay, so you start from 100% silver, you start adding some other alloying element to it, then for the first initial solid solution that forms is called the terminal solid solution because it is very close to the end of that the composition scale that we have. So the terminal solid solution that forms will typically have this structure FCC of the parent material because it is still a solid solution and this is what we have. So in both silver and copper, the terminal solid solution is also typically FCC structure. Then as you start adding the alloying element, you will cross some composition, some particular percentage of the alloying element that you are adding, at which point the structure changes to BCC. Okay, so the structure changes to BCC. So this is a this general trend is seen for silver as well as for copper for a number of binary systems based on silver and copper. So this general trend, you start off with FCC structure, the terminal solid solution is FCC. As you start adding more and more alloying element, it changes to BCC. Now the point is the exact composition at which this change occurs, this crystal structure change occurs. The exact composition at which the crystal structure change occurs varies from system to system, varies depending on the alloying element. The other element in the binary, the element in the binary, the other the element is by definition binary means you have only two alloying elements involved, so silver or copper is one of them, and then you are adding some other alloying element. So based on the alloying element that you are adding at some particular composition, some particular percentage of that alloying element, this change in structure occurs from FCC to BCC. So this is seen in silver and copper, but the and as I mentioned here, the specific composition at which this change is occurring is varying, will vary somewhat depending on the element that you are selecting. Okay, so in that sense there is no great mystery there. I mean, in the sense you look at various systems, you add elements and changes occur at various compositions. So up until this point I do not think there is anything immediately standing out that attracts our attention. At this moment there is no immediate pattern that is showing up here, except for the fact that there is a change in structure from FCC to BCC as you add an alloying element. Now the interesting thing that comes up here is that these systems were looked at closely to see if there was something more common to them which indicated some specific reason for this change. Okay, and what was found was that based on the alloying element, see, based on the alloying element, first thing that you could do is assign a valence. So you can assign a valence state to that alloying element based on what you know of the alloying element, what is its standard valency that it displays, you can assign to it. Okay, so these are substitutional solid solutions, by the way, and so you can and based on what you know of those elements, you say that specific elements tend to show a certain valency. So you can assign a valency to the alloying element. And then therefore you can calculate the what is called the E by A ratio. Okay, what is this E by A ratio? It is the ratio of the number of electrons per atom. Okay, number of valence electrons per atom. Okay, so you have silver and it will have some valency, you are adding another alloying element which has a different valency. So you can take a weighted average of these two valencies based on the number of moles, say based on the molar ratio of how you have added these two elements. Based on the molar ratio of these two elements that you have added in the alloying system, you can take a weighted average of the valency of one atom versus the valency of the other atom. So you can get an averaged valency on a per atom basis, right? You can get an average valency on a per atom basis. It is fairly straightforward that way. So if you have valency of 2 for one atom and 3 for another atom, and you have put a 50-50% mix, then on average it is 2.5 per atom. So that is the way you would do it. Okay, so so that is the way. If it is more towards the atom that is with valency 3, you will get the average valency will be closer to 3 or closer to 2 if you are using the other more of the other atom. So in principle you can calculate an E by A ratio which will take into account the valency of each of those two atoms as well as the mole fractions of the two atoms being put in, right. So on a per unit volume basis, whatever, so you calculate E by A ratio, this is on a per atom basis. So per atom basis we are getting the E by A ratio. So we can assign a valency to the alloying element and we can calculate the E by A ratio or the number of valence electrons per this is the average, okay, number of valence electrons on a per atom basis. So appropriately weighted average we get, so you can get this. This is where the problem becomes, the situation becomes interesting, because we find that regardless of the alloying element that you are using, okay, regardless of the alloying element that you are using, we find that for a specific what we found was the composition at which that change occurs from FCC to BCC is varying from system to system. So depending on the alloying element that you use, the composition at which that change occurs from FCC to BCC can be a different composition, right. But with respect to E by A ratio, we find that the composition change, I am sorry, crystal structure change and therefore the phase change, because the crystal structure is part of the definition of a phase, the crystal structure change and therefore the phase change occurs at specific values of E by A ratio, okay. So this is a very specific value of E by A ratio at which this change is occurring at in the crystal structure, and the composition corresponding to it may be different. That is simply because the valency of that atom that you are adding is different, okay. So the valency is different, and so you may have to add a more of one atom to get the same E by A ratio relative to some other atom. Given that you are starting with copper, if you add one alloying element which has some valency as opposed to another alloying element which has twice that valency, obviously you have to add half as much of the second alloying element to get the same E by A ratio, right. So therefore composition wise these two can differ. You may have to add 10% of one element, you may only need to add 5% of another element to get the same E by A ratio, because their valencies are different and the copper valency or the silver valency is the same. So so the crystal structure change is seen to occur at specific values of E by A ratio regardless of the alloying element that you are putting. So this therefore means that something about the electronic structure of those compounds is creating a situation that one phase is more stable than the other phase, and that is the fundamental reason why these phase changes are occurring. So these phases are therefore called electron compounds. These phases are also called they are also called Humerau phases. And since they are something associated with the electron and electron structure of that material that seems to be impacting the phase change, these are also called electron compound or electron phases. So this is how these names come. So now so this is the general phenomenon that exists. So this has been known for a while. So we would like to see now, given that we have some theories for the material and how the material behaves and so on, and what causes the material to have features in the material, we would like to see if all the theory that we have built or some aspects of the theory that we have built helps us understand why this is occurring, alright. So this is what we will do. So what we will do here is I will make a plot. On the x axis we have energy, on the y axis we have the density of states, right. So this is what we have, density of states and energy, and we will say that at particular values of energy we are reaching the Brillouin zone boundaries and such. So what will happen is, normally if it were a free electron system, if it were a free electron behavior, we would see a parabola. So I will just continue this like this. So this is what the parabola is, okay, corresponding to a free electron. Now given that these free electrons, we are always now given that we talk of solids, we are talking of nearly free electrons and so on, we have already examined the fact that when you have a Brillouin zone boundary, the free electron parabolas are distorted, alright. So they are distorted. So what actually happens is, so they get distorted for two reasons. One, you have and of course this is just the density of available states, the actual density of occupied states will also include probability of occupancy and so on. So that we have to include probability of occupancy here. If this were density of occupied states, this would drop abruptly down to 0 at the Fermi energy. On the other hand, if it were some other temperature, it will have some feature corresponding to how it drops to 0. So that is another parameter we have to add. Now given that the E versus K relationship distorts at the Brillouin zone boundaries, what you actually see is a behavior that looks like this, and the fact that at higher temperatures it is not going to abruptly drop to 0. you see a behavior that looks like this. It is like a free electron parabola up to some point, then it distorts from there and it comes down like this. This is then the density of states as a function of energy that actually exists in that material. Okay, taking into account the fact that you have features corresponding to the E versus K relationship. You also have the fact that your temperature is at room temperature, it is not at absolute 0. All those things taken into account, plus the bands from various zones and so on, which you see a final picture that looks like this for E versus K. So, if you see now, this is actually the density of available states as a function of energy. Now you fill this up with electrons. Okay, so supposing you have filled it up with electrons, supposing you have 1 electron per atom. So E by A or E by A is equal to 1. Okay, it turns out that in systems such as this, E by A equal to 1 would result in electrons occupying states up to somewhere up to here. Okay, so up to here somewhere is where the electrons will exist. So this is what would be occupied if you have an E by A ratio of 1. On the other hand, if you have an E by A ratio of say 1.5, okay, if you raise the E by A ratio to you have 50% more electrons on a per atom basis. So E by A ratio becomes 1.5. This is on average, obviously. So this is on average. So if you do that, what will happen is it will actually go past this peak that you see here, and it would actually fill up to somewhere up to here. So this additional thing will get, so this is up to E by A equals 1, and additionally you will add this. So this whole thing would now be E by A up to 1.5. Okay, so this is what we have, E by A equal to 1, this comes up to here, E by A equal to 1.5 comes up to here. Now please note that there are the number of available states has this form. So actually the availability of states begins to climb up kind of sharply very close to the Brillouin zone and then drops down abruptly. Okay, so that is how we see the available states present within the system, and then it begins to drop down. So this is the general this is the general form of this material or of this information. So this is the form of the information, and based on the number of electrons we fill up those available states in this manner. You could either fill it up to here if you had an E by A ratio of 1, or you would have more than E by A ratio of 1, then you would have up to 1.5. You will see taking into account all the distortions and such, you will find that you are filling it up to here. Okay, so this is the situation. Now so this is and you are starting from a terminal, you are starting from an original material that is FCC structure, so that dominates. So if you actually fill this up for an FCC material, this is how it will look. So on a similar diagram we will actually additionally add what might happen if you plot the same kind of information for a body centered cubic structure of the same material. Okay, so this diagram is the same as what we just drew. So we will have, this is for, let us say now this is for the body center, this is for the face centered cubic material, face centered cubic face, FCC face. Okay, so this is for FCC. FCC face is this, it is showing you this curve. This is just a trend line from the free electron parabola so that we can understand what we are doing. Now for BCC, based on where the Brillouin zone boundaries are for BCC, what we see is with respect to for BCC, if you did the same kind of a diagram, what you will see is it will continue with the free electron parabola a little further, okay, and then it will sort of climb up here and then drop down. Okay, so actually we will slightly exaggerate. Okay, this should okay, we can, I think this would still, we will exaggerate this a little bit so that it is clearer to follow what we are doing. Okay, so an FCC would sort of show you this is the FCC structure that does this. When you do for BCC, the body centered cubic structure, it does this. Okay, so the face centered cubic structure does this, or rather has a number of available states as a function of energy given by this the diagram that is shown here, and then when you draw the same thing for a BCC structure, it looks like this. Now supposing you have 1.5 electrons per if E by A is equal to 1.5. Okay, if E by A is equal to 1.5, we have already seen that in the original FCC structure it would fill up to here. Okay, so up to this energy level, so this is what would get filled up. Okay, if you use the FCC structure, which is the parent structure, you started with that, that is the terminal solid solution, and so you are building up on the terminal solid solution, you arrive up to here. On the other hand, if you use the FCC, if you use the BCC structure, the curve you have to follow is like this. So if once you cross this point here, right, once you cross this point here, you have the number of states corresponding to BCC is actually climbing. Okay, as a function of energy, since you are now you are approaching the Brillouin zone, the Brillouin zone shape is different, the location of the boundaries are different and so on. So therefore it turns out that for a BCC structure, this is where it begins to distort. So when you cross this energy point, some energy value here, so some arbitrary, and we'll just call it EA, okay, so E subscript A. When you cross E subscript A, EA, what you find is that for the FCC structure, the number of states per the density of available states as a function of energy is a function that is decreasing. Okay, it is decreasing in this place. Up to here it was increasing, it increased sharply, started decreasing, keeps on decreasing. So for the FCC phase, once you cross this point, it is already decreasing from here, but it goes below the free electron parabola around there. Okay, and then continues down. For the BCC structure, on the other hand, again it follows the free electron parabola up to some point and distorts and then continues to climb. So you find that there is a small region of energies. After that, even the BCC structure has its density of available states beginning to drop, right, but there is a small range of energies where the density of available states for the BCC structure is climbing, continuing to climb, whereas in that same range the density of available states for the FCC structure is decreasing. Okay, so this is very important to note that the density of available states for the FCC structure has already started decreasing and is continuing to decrease in this range, whereas that for the BCC structure was increasing, and specifically in this range it is continuing to increase, whereas this is decreasing. Therefore in this range of energies, and actually a little beyond this range also, starting in this range of energies, more number of electrons can be stored in the BCC structure for the same same amount of energy compared to the FCC structure, right. So supposing you take 100, supposing let us say this is 1000 electrons, okay, so you have to go up to energy this EB, from EA you have to go up to EB to store those 1000 electrons, just for some random number that we are using for discussion. So you have to climb up to EB, because that is when you get 1000 states available to you to fill up those 1000 electrons. Okay, but if you look at the BCC structure, because more states are available in this region compared to the FCC structure, you may only need to go up to EC, some arbitrary, I will just draw it here, some EC here, to accommodate the same number of electrons. So we are only looking at the okay, so if you just see now, okay, so in the FCC in the BCC structure you are able to accommodate more electrons in a smaller energy window relative to the FCC structure, simply because of where the turnoff is occurring, where it is beginning to change shape. Okay, so it is simply a matter of area under the curve, if you want to look at it that way. The same area in this curve can be accommodated in a smaller energy window. So if this is 0, so 0 to EC is smaller than or effectively EC is less than EB. okay. We are taking the same number of electrons, we are just populating the number of available states, simply because the number of available states is higher for the BCC structure in this energy window relative to the FCC structure. You are able to accommodate the electrons in a lower number of energy values than relative to the FCC structure. So and ultimately, you know, the one of the fundamental driving forces for how things occur in nature is minimization of energy, okay. So that is basically what is occurring. So therefore we see that even though you start with an FCC structure, as you start increasing the number of electrons per atom, you reach a stage where simply because of the energy associated with those electrons, okay, so the energy associated with those electrons, we find that one structure corresponds to a lower energy for those electrons relative to the other structure. In this case the BCC structure corresponds to a lower energy for those electrons relative to the FCC structure. Therefore on the basis of the lower energy being attained for the electrons in the BCC structure, BCC becomes stable. Okay. So we see clearly from our own diagram, from the diagrams that we have drawn for these systems, from all the understanding that we have gained here or in this course, we see clearly how a certain type of a phase change occurs as a direct result of what we can see on these diagrams, okay. So it turns out that in fact this ratio for these systems works out to about 1.4. If E by A is less than 1.4, then it remains as FCC. If E by A is greater than 1.4, it becomes BCC, okay. And so you just have to actually find that 1.4 might work out some particular location, okay. So some particular location here you will be able to get that 1.4 as some particular point here, where it really depends on exactly where this curve is going up and exactly where that curve is coming down. There will be one particular point where both of them can hold the same amount of electrons at the same level of energy. After that the additional electrons will be held in lower amounts of energy by one structure relative to the other structure, and therefore that structure becomes stable, okay. So therefore we see a very interesting set of phase changes which corresponding to these electron phases and what are called these Humero 3 phases as something that we can directly understand and explain on the basis of the theories that we have learned, okay. So this is an important thing that you can read up more on electron phases and you will see how that happens. Now we have an additional thing that we will look at, which is not for most of this course we have actually focused on the electrons. We have focused on the electrons, how they behave, what happens to them, what are the conditions under which they that they experience, what is their response to those conditions and so on. As I mentioned, you know, some of the properties of the material can be directly related to these electrons, and in many aspects of electronic materials and even many aspects of material science and engineering, these electrons therefore form a very important aspect of how the material is responding. The other important constituent of the material is the atoms, okay. So far we have sort of ignored the atoms, and I would like to introduce you at least to one of the concepts associated with how the atoms are behaving with respect to energy, because that also is a contributor to some of the phenomena that we see, okay. Now in the structure of the solid, you have atoms at specific locations. alright. So this is how the atoms are, and around this is the free electron cloud, and mostly we are focused on the free electron cloud. But what happens is that these atoms are not really static, they are not just sitting at exactly specific locations. Instead, based on the energy available to the system, in fact they are in a position to move, okay, they are in a position to vibrate about their mean position, and this is an important way in which they gain energy from as you raise the temperature, and they also release energy as you lower the temperature. So atoms are in a position to participate in energy transaction processes, and they are actually, in terms of an entire crystal, if you take an entire sample full of atoms, they are actually vibrating. So they are all vibrating, they could be vibrating longitudinally, they could be vibrating in a transverse direction. So okay, so all these waves are possible in a material. These waves of and in the process, energy is getting transferred, it is getting transferred from atom to atom, it is going from one end of the material to the other end of the material and so on, and most of these, since they are matter waves so to speak, they all occur at the speed of sound. Okay, so this is speed of sound. So the transfer of energy and such that occurs through these waves occurs at the speed of sound. So in that sense, we are looking at something that is different from what we have traditionally looked at, where we are looking at speed of light in many of the in some of the discussions that we may use. So this is speed of sound is where this information or energy is getting transferred, and these matter waves, okay, as they are called, the waves of this matter, they can also actually be converted to, in principle some arbitrary wave can go through this, okay. So an arbitrary wave can go through it, but we can analyze the arbitrary wave by looking at it as a set of waves, as a sum of waves where each wave has a fixed wavelength, okay. So any arbitrary wave that you take, that is what you do when you do Fourier series, Fourier analysis, you take some arbitrary waveform, and that waveform can be actually obtained by summing up a series of well defined sinusoidal waves, okay. You just have to take those sinusoidal waves, specify their amplitude, specify any phase differences if necessary, such that they all add up to give you this arbitrary waveform that you have. So similarly, any arbitrary waves that is passing through this structure can be thought of as all of those waves that are adding up to give you this arbitrary wave. So these matter waves are referred to as they are given a name, and they are referred to as phonons, okay. Phonons are waves of lattice vibration, okay, waves of lattice vibration, these are phonons. They are of interest for several reasons. First of all, for example, when we talk of specific heat of a solid, we in all our calculations we kept focusing on the electronic contribution to the specific heat. What about all the atoms? The atoms also contribute to specific heat, and in fact they do so in the through this when they do so, the energy in the atoms is that you are providing to those atoms is held there in the form of those waves that are present within that system, okay. So therefore when you analyze the solid for specific heat as an overall concept, you have to look into the phonon contribution to those that specific heat, okay. So that is how we get the overall specific heat of that solid. So phonons are these lattice vibrations. Interestingly, the energy of a phonon is also still related by this equation E equals h nu. So in that sense, actually these phonons are in fact represent one region where you can actually see one region in our discussion so to speak, where you can actually see quantum mechanics very successfully explaining some of the behavior shown by that solid, okay. So they too are absorbing energy. See, they are also waves, they are and they have energy associated with them, and it turns out that they also accept energy only in step functions, just the way we look at photons accepting energy only in steps of h nu. Phonons also accept energy only in steps of h nu. Only difference is, as I said, they are traveling at speed of sound. So this nu here is v sound by lambda, okay. So that is a very important difference, v sound by lambda, and so that is how they do. So they are quantized, so that is a very important thing. So the phonons are the are the lattice wave equivalent of photons. Okay. Just the way we talk of photons for light, we talk of phonons for waves in the crystal lattice. Okay. So they are analogous, so to speak, in terms of what they represent. So when it is light and electromagnetic radiation, we talk of photons. Okay. So that is what we have done for most of the course. We have spoken about photons, but in the lattice we have phonons. Okay. So this is the thing, and they participate, like I say, in things like the specific heat, for example, is explained on the basis of phonons. The change in specific heat as a function of temperature. There is there's a Dulong-Petit law which says that specific heat is a certain fixed value for all solids, but actually if you look at specific heat as a function of temperature, then it does have, as you get to lower temperatures, it does have a certain change in its form as a function of temperature. It is not a fixed value, and those are explained on the strength of phonons and what frequencies they can hold. Okay. So that is how you explain certain things, but also very importantly from our perspective, there are even the electronic transitions that we talk of are sometimes assisted by phonons. Okay. So there are times when electron transitions are occurring which are directly associated with phonons, and we will discuss that briefly. I just want to point out that in a crystal lattice, when you talk of phonons, there is some restriction on the wavelengths that they can look at. We can look at clearly, as we have done before. If this is the length of the material L, okay, the highest wavelength that can be supported in this L is such that this is half the wavelength, that this length is half the wavelength. So the atoms form half a wave here, and the other half is outside, so to speak. So this can define half a wavelength just the way we did before. So L can be or 2L, lambda can be 2L, lambda maximum equals 2L, where L is the extent of that solid, so to speak. Okay. So that is the maximum that you can get. The minimum, so if this spacing is d, inter-atomic spacing is d, so lambda minimum is 2d. Okay. So this is what you will get. In between, basically you will get, if this is 2L, the next one, so you can get lambda is equal to L by 2, I am sorry, lambda is equal to 2L, and then you get the next one you will get is lambda is equal to L, and so on. We can get different possible wavelengths in this solid, going from the 2L to the 2D limit. So this is what you will get, right? And also if the atoms are so to speak, if the atoms are actually if you actually have a 2 atom basis on your unit cell, and let us say those and it is an ionic crystal, if it is an ionic crystal, what you will have is, when you do this kind of a flipping, you are actually changing the field as a function of time. So it is sort of creating an electromagnetic response, so it can actually interact with infrared radiation. Okay. So some of these phonons are what they call optically active phonons, because you can send infrared radiation and the material will respond to that infrared radiation. So some of these phonons are optically active, the others are acoustically active because they are talking of sound. So that is how these phonons differ from each other. Okay. So this is how they look, and as I mentioned that they actually interact with electrons and allow certain transitions to occur. So for example, we looked at direct band gap versus indirect band gap materials, right? So in a direct band gap material, the highest so this is K, this is E. So this is one possibility, that you have the highest level in energy of one particular in a particular band at the same location as the lowest energy of the next highest band. So therefore you only need to provide a photon to get this electron to go up here. With E equals h nu, E band gap equals h nu. So you provide this, then you can get the electron to go across. On the other hand, if you have a structure where this is K, this is a band, and we will say these are filled, okay. So this is filled, so this is also filled, that is empty, but at some other location in K space you have an even lower band, right. So now actually instead of you need less energy, this band gap is smaller than this band gap, only difference is this is at the same location in K space, this is at a different location in K space. So the electron needs less energy to go up here, this is a smaller Eg, but it will not suffice if it goes here, it has to go across to this location in K space. So it has to sort of go up and it has to go across. So two things have to occur, okay. So it has to go up and it has to go across. This occurs using a phonon, so this is phonon based. The lattice vibration enables the electron which has gone up to which is gaining energy to also get to the right location in K space so that it can get into that band, okay. So for an indirect, so this is direct band gap, this is indirect band gap, and what we see is for a direct band gap photon is sufficient, photon with enough energy is sufficient, with appropriate energy is sufficient. Whereas for an indirect band gap semiconductor you need a photon plus a phonon. Okay. So the thing is, when you talk of photons and phonons and such, they are all present in the system, they are all occurring at different points in time. So there is a certain, at a given instant, see when you look at this kind of a system, light is falling on the system, let us say, okay. So and you would like to see if some transition is going to occur or some energy is coming, transition, in this case light is falling on the system, you want to see if there is a transition that is going to occur. Will it occur for a specific electron? That is the question, okay. For a given electron will it occur? Whether or not it occurs for a given electron is simply there is an element of chance, so that photon has to strike that electron, so there is a certain probability associated with it, okay. So there is some element of randomness in this process. Photons may be going all over in the sample, they may be striking something else, something else might be happening. So a certain photon has to arrive and get in, effectively interact with a particular electron and then enable that transition. So there is a probability associated with that. Again similarly lattice waves are travelling through the system, and so the right kind of a lattice wave should be available for that electron for it to go from this location in K space to this location in K space. So for each of these things there is a probability associated with it. So here you only have the probability associated with the interaction with the photon and the electron, so that is certain probability. When you look at this system you need the interaction of the photon with the electron, there is a probability associated with it. Immediately after that you also need the interaction of that electron with the phonon, okay. So there are two separate steps that are occurring here, both of them have a probability associated with them. So therefore the probability of the whole thing occurring is the product of these two probabilities, okay. So and therefore this decreases in probability in a very significant sense, okay. So because these are all some probabilities associated with them, you are multiplying them and they are all they are not close to 1, they are much less than 1, therefore when you multiply the probabilities this drops in a very big way, okay. So what happens is, the point I want to highlight here is, it may be that for an indirect band gap semiconductor the band gap is small, okay. In fact you will find systems where the indirect band gap semiconductor, this is what is defined as the band gap, the highest occupied state versus the lowest unoccupied band energy level. So this gap is now the band gap. So this band gap may be less than this band gap, okay. Still when you supply light to these systems, the probability of this transition across this band gap will be less than the probability of transition across this band gap, because of the fact that phonons are involved in this interaction process. As a result, for optical properties direct band gap semiconductors are much more effective, okay, than indirect band gap semiconductor. So if you are talking of how, I mean the number of times this transition occurs and similarly the number of times the transition backward occurs defines the amount of light you can get out of the system, okay. So you have raised all the electrons, if they begin to fall back they release light, you see the light. The intensity of the light, the intensity of the light depends on how many of these electrons are going through the process. The energy of the light is the same because that is defined by the band gap, okay. So here energy will be higher, but you will get a very weak beam in terms of the intensity, it will be a very dull beam, you will not be able to see enough with it. Here the intensity will be nice, you will get a very nice intense beam because I am sorry, here you will get a dull beam because you have to get a two transactions have to occur. Here you will get a bright beam because you are getting double advantage here, okay. The band gap is higher, so higher energy is there, at the same time the probability of transition is also high, so therefore you get a higher energy beam which is also intense. In this case you get a lower energy beam because the transaction is less, but on top of it the intensity is also less because it is a two step process, okay. So that is two step process is reducing the chances that it will occur, you get a dull beam. So for this kind of a process where you are using electronic transitions to get light or interaction with light, these are called optoelectronic materials, okay. So optoelectronic materials is what we are looking at. So for optoelectronic materials direct band gap semiconductors are considered very good as opposed to indirect band gap semiconductors. As we saw in the last class, gallium arsenide is an example of a direct band gap semiconductor, silicon for example is an example of an indirect band gap semiconductor. So for optoelectronic processes you use direct band gap semiconductors, okay. So this is one thing I wanted to point out, and I want to also finish off with one other detail which will now lead us to what we will discuss in fact in the classes ahead, a couple of classes ahead, that is that we spoke of particles, the statistics associated with particles and so on. More specifically when we spoke of electrons, we started off by saying electrons are we started and treated them as classical particles, we used Maxwell-Boltzmann statistics. Later we recognized that maybe that was not the right thing to do, we tried out a quantum mechanical approach where we used Fermi-Dirac statistics for electrons, okay. And the validity of using a statistic for a given particle really depends on the characteristics of those particles. So you and that is the reason why Maxwell-Boltzmann statistics fails and Fermi-Dirac statistics succeeds for electrons, because they have all the characteristics that the Fermi-Dirac statistics is assuming about that particle. Similarly particles or particles such as photons and phonons follow a statistical behavior which causes them to be called bosons, okay, and therefore they are called bosons because they follow the Bose-Einstein statistics. Okay, so they follow the Bose-Einstein statistics, so they are called bosons, and therefore that is what defines how they behave and so on, and this is also defines how they interact with the various systems and various phenomena around them, okay. So we will see in the next class, the next couple of classes we will certainly in our next class we will look at another phenomenon of material behavior where some again the interaction of a phonon will become necessary, okay, and phonons are bosons. So we will actually and certain aspects of what we will discuss in the next class will be related to the fact that certain particles will behave like bosons. So we will look at the phenomena, in fact we will talk of superconductivity in our next class, and we will first look at superconductivity as a phenomenon, and then we will also discuss since in a couple of different contexts it will involve talking about bosons. We will in the class after that we will look at Bose-Einstein statistics or the bosons, and that will help us understand certain aspects of it. So to sum up, in today's class we have been trying to look at more places where the theories that we have developed, the understanding that we have developed helps us follow various aspects of material behavior, and in this regard we looked in reasonable detail at the electron compounds, what causes them to occur, how the diagrams we have drawn enables us to understand why these compounds form, or what is the phenomenon that is defining the formation of these compounds. So we saw that in great detail. We have also additionally added on to our understanding by looking at phonons, we have looked at crystal lattices and the fact that waves could travel through those lattices. Those waves are quantized in their energy, and the particle equivalent of those waves is called a phonon, and in that sense it is analogous to a photon, and we have related it to something that we already discussed, which is the direct and indirect bandgap semiconductors. We looked at the fact that for optoelectronic purposes direct bandgap semiconductors are better because they do not involve phonon based transactions, whereas indirect bandgap semiconductors will suffer for that reason because they will involve phonon based transactions. So the probability of the transaction decreases. So you cannot go only by bandgap. The bandgap helps you decide that which has more energy, which has less energy, and in some cases either of them might have a higher or lower energy when you compare a direct and an indirect bandgap semiconductor. Additionally, we also have to look at the probability that the transition will occur, which occurs and that probability is much higher when you look at a direct bandgap semiconductor. So with this we will halt today in this class, and in our next class we will look at superconductivity as a phenomenon. Okay, thank you.